So I will discuss today the control channels that you will see in your various quantum devices. There are broadly two groups of people here in the audience. There are people who do laser spectroscopy and optical control, and people who do spin physics and magnetic control. So you have two different sets of operators, and at this point we need to discuss them in significantly more detail than what you would have had in your undergraduate courses. So starting with the electric control operators, so electric fields, control, that would normally be the plane wave emitted by some laser that would be hitting your molecule and causing some transitions. Now you may remember from your undergraduate physics course the really basic observation that the energy is minus d dot E, where d is the dipole moment of the molecule and E is the external electric field. And then if you have, for example, a pair of separated charges, then that was minus ER, right? The charge and the distance between them. And this is what all chemical spectroscopy, UVVs, and so on were based on. You were just given that as a reasonable quantization of a reasonable interaction. But of course, what you can see here immediately is the further away you pull the charges, the greater this becomes until it goes to infinity. And if you think about how many charge-separated states there are in the universe, you would start suspecting that maybe this is not the whole story. And in fact, this is an approximation, and we need to discuss the nature of that approximation. Right, so I start with the basics. If we have a molecule that is only exposed to an oscillating, so plane wave, an electromagnetic field, and there are no other static electric fields around it, what we're going to have is the vector potential that corresponds to that electromagnetic wave will be some amplitude term times a cosine, and here we would have two types of frequencies. We would have the spatial frequency and the temporal frequency. So you would have the wave vector times the direction minus omega t. So that is the spatial direction and the spatial frequency, and that is the temporal frequency part of that. And I would remind you that k, the modulus k, is related to the wavelengths of the particular wave, and then of course the wavelength is related to the frequency by the speed of light, right? So w is ck, lambda in here, c modulus k. And so that's the standard electromagnetism for you for now. What we do when we put that into a quantum mechanical description of the molecule, we use the so-called minimal coupling, which is the Lorentz invariant form of the momentum operator. We have our usual momentum, which, as you hopefully remember, was minus I d by dx y z. So d by dx, d by dy, and d by dz. Transpose in here, usually it's a column vector, but what we replace it by is the generalized form, which is p minus qa, where a is the vector potential and q is the charge of the particle whose momentum we're looking at. And then of course for us the charge of the electron is negative, so we say okay, that's p plus ea then, where E is the elementary charge, which in SI conventions is positive by definition. So we do flip the sign in here. And then we put this all into our standard Hamiltonian. So remember what we had in the original Hamiltonian. That was essentially mv squared over 2, so momentum squared over 2m plus some external potential that may depend on the location. So what this now becomes is, instead of p squared, we have pi squared, so that will be p plus ea squared over 2m plus b. function of location. Let us open this up, substitute in our electromagnetic plane wave, and take a look at what we get out of there. So, opening that up, we will see a bunch of terms that we already saw. Firstly, in your standard quantum mechanics course, and secondly, in the first part of this module. So when I introduced magnetic interaction calculations with electronic structure theory, we actually discussed a significant amount of stuff that you will now see here. So we have p squared over 2m, the usual mechanical momentum term, plus our v of r, and this is just the original background Hamiltonian that we are not interested in, that goes into H naught and acts in the background, right? This determines the electronic structure of the molecule. Then there will be two further terms in there, so 1 over 2m. And remember, in quantum mechanics, things do not have to commute, in particular because this thing acts on a wave function, so there's like an imagined psi in front of it, so you have to be careful when you're opening up those brackets. So what we're going to have in here is, I will put E in front as well, then there's P dot A plus A dot P in there, so the interaction between the momentum and the vector potential. And finally, we have the E squared A squared term, so we would have E squared over 2m A squared. So this is not interesting. This is our molecule as we had found it before the electromagnetic wave had hit it. And this, for our purposes, is not interesting because from the point of view of it being hit by an external electromagnetic wave, this is usually negligible. So, negligible. You've seen this being important inside the molecule itself, where the electric and magnetic fields are much stronger, right? Nuclei moving electrons at very close distances, femtometers or thereabouts. Then that matters, and you've seen this contributing to things like the J coupling in the first part of this module. But here, to us, at least for now, this is not interesting. What is interesting to us is this term, because that is the interaction of the momentum of our electrons with the vector potential. So, and this is, I will call it H int, right? The interaction Hamiltonian. So let us take a look at it and have a discussion. The first thing we will notice is that the wavelengths of typical light that we shine at our molecule with a laser. So UV is around 100 to 200 nanometers. Then Vis is between 200 to about 1000. That's where the infrared is, nanometers. That is a very large number on the molecular scale. Remember, CH bond is about 1 angstrom across. And so that is 0.1 nanometer. So the wavelengths of light that we have is 1,000 to 10,000 times longer than the length of the typical bond. So we have our CH, and on the scale of a typical CH, double bond, rubidium atom and some vapor, for all intents and purposes, the spatial slope of the electromagnetic wave is negligible. It's as good as constant with respect to location on the length scale of a typical molecule. And so the first thing we assume is that for the R, that we will realistically encounter, at least in small to medium-sized molecules, K dot R is negligible here. And then, of course, it's a cos, so the minus becomes a plus. But what is more important is that A stops depending on location and only starts to depend on time. So our, what was previously A, R, and T becomes just A of T. Right? oscillating in time, but quasi-constant on the time scale of the molecules we would realistically be dealing with. What this then means is that A commutes with P. Remember, P contained spatial derivatives, d by dx, d by dy, d by dz, and A now is a pure function of time. So that is not a function of location, and so we can interchange the derivatives and the functions of time, no problem. So this, in fact, is the same term. We can just merge the two here and remove the 2 from the denominator. So our h int, as a result, here h int, let me see which way around, I've chosen it in the lecture notes. This is now E over M, and then P dot A of t, right? Remember that both are in fact vectors, because that thing can point in different directions in space. Although, wait a bit, yeah, that's right. Now, the next thing we will observe here is that this interaction Hamiltonian is nowhere near the interaction Hamiltonian that we expect here. Notice that's the coordinate operator here, and that's the electric field. What we have here is a momentum operator interacting with the vector potential, right? Clearly, there's a considerable mileage between here and here, which we now have to cover. The derivation I will now give you has subtle inaccuracies in it. It is somewhat an abuse of notation. This is because the full derivation is horrendous. So in 10 years' time, when you look at these lectures again, you will realize that Kuprov has fudged it somewhat, but for now, just take my word for it. So what we will now do is, firstly, from Maxwell's equations, in the absence of the static potential, which we have tucked away into there already, we will observe that the electric field as a function of r and t is minus dA of t by dt, right? The derivative of the vector potential. That's what remains of Maxwell's equations in our particular chosen gauge. So we have this derivative with respect to time. The second thing is that this p is the derivative with respect to x, and let me remind you that in classical physics, P was mv. So what I will do is I will cheekily replace this momentum with a velocity operator. And then I would observe that in classical physics as well, velocity was d by dt of x, all right? This is quantum mechanical. This is not quantum mechanical. This is a classical relationship, but I will still use it here. So our h int would then become, so I will put E, then we have the velocity operator, and then we would have A of t there. Now what I'll do is I'll differentiate the following. So as an aside, maybe at the bottom in here, I'd say d by dt of r dot a of t is going to be, and that's just the standard product rule. So we have dr by dt times a of t plus r dot da by dt. Right? And then let's take a look at what we have there. We have v, which is dr by dt times a. So we do have that term here. So what I'll do is, instead of that term there, I will put this minus this. So that's going to be E times d by dt of r dot a of t minus that r dot dA by dt. Okay, the second observation that I will make and not prove, because the proof is very long and tedious, is if you have a full time derivative of something inside the Hamiltonian, the only thing it creates is an overall wave function phase. And as you know, observables do not depend on the phase. So it's a gauge transformation. Right, so that we can gauge away. No proof. Take my word for it. You can look up the proof yourself. If you have a full derivative in the Hamiltonian, the only thing it does is to put an overall phase on the Hamiltonian. Okay, so we now have that, and of course minus dA by dt is E, and so we can continue that. Minus cancels with that minus, we have ER dot E of t, which is a lot closer to what we need, which is in fact minus d operator dot E, where the d operator is minus ER, right, vector operator, both of them, here and here. So that is the derivation. Now notice the assumptions that we have made here in a few places. First, we have ignored the a squared, which in strong electric fields might not be negligible, so beware if you are running it on some free electron laser with some super intense electric fields. The second thing that we have observed is we say the molecule is much smaller than the wavelengths of light. This is okay for visible light and ultraviolet, but not okay for X-rays and gamma rays. So, or in situations where the molecule or an atom like a Rydberg atom is actually comparable to the wavelengths of the light that it hits. And then this gauge transformation is in fact exact, even if we fudged it somewhat. And this in practice is your control operator, right? You do control the electric field. It then enters your Hamiltonian as a time-dependent interaction, and we then can steer chemical reactions, for example, by hitting the molecules with lasers, and there is, 100 or so years of literature on the subject. So we will be dealing in particular with interaction operators like that. Right, that is the electric field part. Let us now take a look at the magnetic part, and the magnetic part's even worse. So, magnetic. Zeeman interaction. And my girlfriend, who's Dutch, insists on pronouncing it Zeeman because, well, Peter Zeeman was Dutch. So, where we need to begin is at the very, very beginning with Dirac's equation for the free electron. So, same story as before, we do need this minimal coupling Hamiltonian, P plus EA. And then I will remind you, or if you're chemists, I will tell you that Dirac's equation in matrix form is the following. d by dt with I h bar in front, acting on two components, psi large and psi small. I'll explain in a moment what that is mc squared c sigma dot pi c sigma dot pi, and then minus mc squared acting on this pair of wave functions again. Right, very roughly speaking, what we are dealing with here is an electron-positron pair, right, or an electron-hole pair, however you would like to look at it. In essence, the energy corresponding to the mass of an annihilating electron-positron pair is predictably 2mc squared, right? When you take an electron and a positron and you annihilate them, you get the equivalent of 2 electrons in mass converted into energy. And so there you got your mc squared, and there you got your minus mc squared, corresponding to the positive and negative, so electronic and positronic degrees of freedom. Needless to say, at the energies that chemists would realistically encounter in their flask, you never have positronic degrees of freedom, and so this psi s will now need to be eliminated. And then what couples the positive and the negative energies is the inner product between spin and this same minimal coupling momentum that we have just discussed in the context of the electric field. And of course, once again, the interactions we realistically have for light elements like carbon and hydrogen are far too weak to ever populate the psi s. It's called small because it's weakly populated, but if you are sitting in the s orbital of, I don't know, plutonium, then that stuff really does move at a significant fraction of the speed of light, and at that point you will have these degrees of freedom. And this is why transition elements, and particularly actinides and lanthanides, are so difficult from the electronic structure theory point of view, that you actually do have these effects kicking in there. But for our purposes now, let's assume we're dealing with a light enough molecule where most of that doesn't matter. Notice I don't have the static electrostatic potential here either, so we're just dealing with our plane wave. So what we will now have is a somewhat simplified version of how one eliminates the negative energies from Dirac's equation and turn it into Schrödinger's equation. And that is something instructive that I would like you to see. Okay, the first thing we're going to do here, and I will do it by the method of erasing and rewriting because there's too much to rewrite, is we will shift the energy reference point. As you know, it doesn't really matter what we consider our zero energy. Again, this is a gauge transformation. The only thing it would add is a phase to the wave function, but we know that the energy 0 point is arbitrary and only the differences are really physical. So what I'll do is I will call our chemistry the reference point, and this will then necessarily be minus 2 mc squared. So this is convenient because this really puts the equations that we do care about at the zero reference point of our energy. So we will deal with that. And then that stuff, you know, oscillates with this giant frequency, right? So this is half a mega electron volt if memory serves. Okay, let us rewrite this vector matrix equation as a system of two just standard algebraic equations. So we have a system, and then here d by dt and minus ih in front, acting on psi l. This one will be psi l is multiplied by 0, and this is c sigma dot pi psi s. Now, that's the first equation in the standard algebraic form. And then the second one, ih bar d by dt on psi s. That one will be c sigma dot pi psi l, and then minus 2mc squared psi s. Okay. Now, as it happens, if you look at the dynamics of this positronic degree of freedom, the full derivation is given in my book in chapter 2, but it oscillates extremely rapidly, the so-called Zeta-Bewegung, the fluttering motion, that has such a high frequency, I don't think it's even been observed. It's only been observed indirectly, right? So this corresponds to some mad amount of frequency, and we can average these equations out. In other words, this, on the sort of time scales that we look at in chemistry, is negligible. So this particular derivative averages out to 0. I will not explain to you how exactly or why. I will only mention that it does. What it leads to, however, then is because this part is 0, we now have an algebraic equation that connects psi s and psi l. In particular, I can express psi s out of it. I could say that my psi s is, move that over here, divide by 2mc squared. So we are going to have 1 over 2mc, right? So 1 unit of c cancels, and then we would have sigma pi from here and then psi l. But that is excellent because I can replace psi s over here. So what this is going to lead me to is I h bar d by dt psi l, that part. Another unit of c is going to cancel here and here, so we have 1 over 2m, then sigma pi, so that is sigma dot pi squared, and then psi l. Notice that this now is actually Schrödinger type equation, and just for the large component. So we have approximately, and I haven't explained to you exactly how, eliminated the positronic degrees of freedom out of Dirac's equation. And so we now have this sigma pi that we need to deal with. And sigma is just your usual Pauli matrices, right? 1 minus 1 and so on. So let's deal with that. In order to deal with that, I will remind you the following relation. So for any vectors a and b, sigma dot a, sigma dot b, so these are all vectors. That's a vector of 3 matrices, that is just a vector. We have a dot b plus I sigma dot a cross b. And let us use this to simplify sigma dot pi here. So we have sigma dot pi times sigma dot pi. So a is pi and b is pi. That gives us pi squared, right? Inner product of pi with itself, and then plus I sigma. And then an interesting thing, pi cross pi, and you know that the cross product of the vector with itself is 0, except this is not a vector, it's an operator, right? There's a wave function in front, and so we first act by this pi and then by this pi, and that turns out to be non-zero. Okay, so let us rewrite now what we have there. So I will drop the equation of motion and I will just focus on this Hamiltonian that we have here. Now our h is 1 over 2m sigma dot pi squared, and we substitute that in, so we have pi squared over 2m. That is our usual kinetic term in the presence of the electromagnetic field, and then plus I sigma and then dot pi cross pi over 2m. In here, there are parts that are not interesting to us because we have already discussed them. In particular, the previous half of this module had a lengthy discussion of what happens in here, right? The orbital angular momentum interacting with the magnetic field, so orbital Zeeman interaction, Langevin susceptibility, and a few other things came out of this term. So look at those PowerPoints from part 1. You will see everything that goes in there. Our part now is to discuss the coupling between the spin and whatever the hell this monster is. So let us open it up and take a look. Now, I remind you what that is. It's the momentum plus EA, and let us go through the various vector calculus relations that would allow us to simplify it. Firstly, P is minus I h bar gradient, right? So the three derivatives with respect to the individual coordinates, like we had there. Secondly, I will remind you that the rotor of any gradient is 0, right? Standard vector calculus relation. For vectors that are literally just vectors and not operators, their cross product with themselves is 0. And of course, we do have the usual product rule for the divergence. So a psi for the curl. So that's vector, that's a scalar. If you work through that, that's psi, then the curl of that minus a cross the grad of psi. And then finally, of course, the definition of the magnetic field in the vector potential picture, in that is a curl of the vector potential. So all of that. So all of these relations we will now need. Let us open that thing up. So continuing here, we have the uninteresting pi squared over 2m plus I sigma over 2m dot, and let's see what goes on inside. So we have p plus EA cross p plus EA that we now need to open. Okay, so now we've got what in here? Let us open that up. So pi squared over 2m plus I sigma over 2m, and in these brackets we have p cross p. That's an operator as well. So we have p cross p, then plus p cross EA, so EP cross A, then we would have EA cross P, and then finally E squared A cross A. And I need a square bracket there. There it is. Okay, as per the observation here, A cross A is 0. Remember that this momentum is the gradient operator. If there's a wave function sitting in there, we have a gradient of the wave function, and that's a gradient. Again, that's the nabla cross nabla psi. That is going to be 0. So that is gone as well. And then we've got these two, and I will explicitly rewrite the momentum in its differential form now. So let us continue. Our pi squared over 2m, then plus. Okay. Minus IH pops out in front, but we already have 1 unit of I, so that all collectively becomes a plus. And then we have the electron coming out in here. And let me see what we've got. So this is now E H bar over 2m. And then we have sigma dot, and now it's nabla cross A plus A cross nabla. Okay, and remember there is a psi implied in front of it. Now what comes into play is this relationship here. So we have a psi in there. So what is going to happen is it will get multiplied into here. All right, so let us rewrite that. We have nabla cross A psi. Right, so that's the psi times first term here. And that will literally be this. So we just rewrite it. So maybe I shouldn't rewrite that equation yet again. I should just simply state that. So in that bracket, we are going to have nabla cross a psi, then plus a cross nabla, and then psi there. We use this relation here, so that will get us psi, then this, minus a cross nabla psi, and then plus a cross nabla psi. Okay, brilliant, that stuff cancels too. Now that's gone and that's gone. And notice what we have here, that's the magnetic field. So that is actually psi b, and since psi is a scalar and b is just a vector, we can write it as b psi. Oh, like that. And of course, now that we've determined that this entire thing in brackets is actually just b, that becomes pi squared over 2m plus EH bar over 2m, and then sigma dot b. All right, but remember what the sigmas were. Sigma x was 1, 0, 0, 1, right? Sigma y was 0, I minus I 0, and then sigma z was 1, 0, 0, minus 1. They were a factor of 2 away from the operators of spin half. So we can absorb that half from here and rewrite that thing, move it there somewhere, as pi squared over 2m plus EH bar over m, spin operators interacting with the applied magnetic field. And finally, if I introduce a few fundamental constants, or magneton, that is EH bar over 2m, and then finally the G factor of the electron. And here, unfortunately, we are not doing quantum field theory, so no radiation corrections to G factor. This will be actually exactly 2 at this level. And so once we put all of that in, that is pi squared over 2m plus G E mu b s b, and that, of course, is the good old Zeeman interaction. That you see in all of your textbooks. And this is where all of the rest of the electronic structure theory takes place. And notice that this, in fact, is perfectly compatible with what we have just derived for the electric field component of that. So remember what we had there. We had our conventional momentum, and it became pi plus the potential. So this is literally what we have here, plus the special relativity has given us the interaction between the spin and the external magnetic field. Okay, so the summary of 2 rather nasty derivations, as you can see. Probably we should start the overview with Dirac's equation, because it kind of gets us to the starting point of our electric field discussion. Those of you who did physics remember this beast. Those of you who did chemistry, take my word for it that this can be derived from Lorentz group, as Dirac, Dirac actually guessed it, it was Wigner that derived it from Lorentz group, and these correspond to the positive and negative degrees of freedom of what is substantially a particle that looks like an electron but can look like a positron if you kick it hard enough. In our chemistry practice, we rarely worry about these negative degrees of freedom, so we shifted the energy offset to put our conventional chemistry at 0, and this is somewhere very high up or very deep, depending on your point of view. Then we said, okay, let us convert that into the standard algebraic form, and then it turns out, and that can be proven rigorously, I did not do it here, that the frequency with which the small component oscillates is enormous. And on the time scale of conventional chemistry, this derivative is therefore averaged out to 0, which gives us the algebraic relationship between psi s and psi l and allows us to eliminate the psi s from the first equation here. We substitute that there, we get our sigma dot pi squared psi l, and now this is just for the electronic component, and of course sigma are 2 by 2 matrices, so this is a 2-element vector that corresponds to spin up, spin down eventually. And now we have to deal with this sigma dot pi somehow, and I've given it to you without derivation. You can just test it really by direct inspection. If you put this sigma x, sigma y, sigma z into there and check that that vector identity is true. We put sigma pi and sigma pi on both sides. Pi dot pi is just pi squared, and then we've got pi cross pi, which is not 0 because pi here is a differential operator. We take our Hamiltonian, we use that relationship, we get our answer there, and this is what we will then start the electric field discussion from, but now we are focusing here. We've opened it up by explicitly putting that there and opening the brackets. P cross P acting on any function is 0 because the rotor of a gradient is 0, and of course the first nabla here is the gradient and second is the rotor. A cross A is 0 because A is a standard vector which has a 0 cross product with itself. Then we've got this momentum and the A, which we've opened up explicitly by introducing the definition of the momentum operator. So it went here and here, and so we now have this. We've done a little bit of philosophy to remind ourselves that there's the wave function in front. So put it in there and use the final vector calculus relationships that I've put into there to realize that this is just multiplicative with what is Maxwell's definition of the magnetic field. So this is B psi. We've put it all back in. We still have this surviving term from here, and now we have an interaction of this sigma, sigma x, sigma y, sigma z with the magnetic field. We looked directly at what those sigmas are, realized that they're a factor of 2 away from the spin operators that we know and love, absorbed the conveniently positioned factor of 2 from the denominator here, turned that into a vector of spin operators, used the usual fundamental constant definitions, and realized that poof, we have our Zeeman interaction Hamiltonian in there. Right, but what about this pi squared over 2? That's where our electrical story begins. So we had our p squared over 2m when we introduced the magnetic vector potential. That became pi squared over 2m, and this we don't worry about. That's just the rest of the molecule. Acting on it, we want our electromagnetic field. If the field is a plane wave like that, we put it into there, open up the brackets. That's the H naught responsible for holding the molecule together. This is negligible for typical electromagnetic fields that you have, so we have this interaction term remaining. We process it a little bit by observing that the molecule is so small that on the length scale of the molecule, the vector potential simply doesn't depend on the coordinate. That means that A of t is no longer a function of distance and therefore commutes with distance derivatives that occur here in P. So we can simplify that further. And then I have done a bit of a hand-waving exercise, which is not perfectly precise. I said in classical physics, velocity is d by dtx. Why don't we use this relation for no particular justification in what is here otherwise operator calculus, and massaged this equation into what previously had been momentum coupled to the vector potential into what turned out to be the dipole moment coupled to the electric field, and this gives us your standard interaction Hamiltonian with the electric field. So the laser people present will be using this to control their systems. The magnetic resonance people present will be emitting various magnetic fields from their radio frequency coils, and that will be interacting with your spins. So these are the two types of operators that then go into your overall Hamiltonian that your instrument can actually vary, and this is how we are going to be steering our quantum systems from the next lecture. Any questions? Oh, look.
So in the pi operator, because we added the electric potential, the Zeeman came out. If we do the calculation without it, just the Schrödinger equation.
It will, yes.
Without it.
That's right. Yeah, it will reduce to Schrödinger's equation.
And we can add we added the electric potential because there will be an electric field, so we can just attach it on at the beginning. Okay.
All right. Yes.
With the hand-wavy classical assumptions, does that, if you were to do it how you do in the book, do you end up with
Long story, so you would need to make more use of this assumption that you effectively have a point molecule. Then that creates a delta function in the descriptions, and then derivatives of delta functions can be shifted between the delta function and the function it acts on. And so the long derivation that you would see in the textbooks makes use of that fact. So it's a bit of a longer story, really. All right, see you on, what is it, Thursday.